Hello everyone, this time I'm just going to show you something quick and interesting in my Excel-based numerical launch trajectory calculator project. Now this is the same calculator that I've shown you how to make before the Falcon Heavy launch and that I made a actual modification on simulating roughly the trajectory of the Falcon Heavy later on. So I've shown that while it's not designed for that, you can do surprisingly much with just Microsoft Excel, and I've shown that you can do quite a few provisorical additions and changes to this to accommodate for things previously not thought of. It's not elegant, it's kind of a bodge, but it works. And now I've added a few more things for this thing. First of all, I've added a few calculations that don't really affect the simulation itself, but they are useful readouts when optimizing a trajectory. They show you some interesting information that you might want to consider while optimizing. So the first two of these additions are drag focused. So this one is the ratio of thrust to drag, as you can see, and this one is the ratio of drag to mass. And that is interesting when optimizing an ascent through the atmosphere. During the initial ascent, you want to keep that drag to mass ratio at something around 1g maybe at maximum, because if you assume a dense atmosphere that just continues forever and you want to efficiently climb up through that, then the most efficient way to go is with a thrust weight ratio of 2 and thus a drag equal to the force of gravity. So that's one thing to consider during the first part of the ascent. However, that is only assuming an infinite atmosphere that goes on at high density. Then when you come to the later part of the ascent, you want to keep this somewhere at 1/10 of a g or something, so that you don't waste too much energy while accelerating to orbital speed, but at the same time don't go higher than you need to. So something like something below 1 in this column would be a good optimization as a rule of thumb. And then this third window is a slightly more complicated calculation that is not really elegant and not really perfectly correct, but it's an approximation of the ballistic apogee at this point. So this is approximately, and ignoring aerodynamic drag, if you shut down the engine at this point, how high will the rocket go before it stops going? And that's interesting to keep the engine running and see where you shut down the engine for a cruise phase and then a later circularization burn. And I've used these readouts and the Falcon model that I roughly made, or the Falcon specs that I entered. However, this is no longer the Falcon Heavy, and it's not really a Falcon 9 either. This is a Falcon 9 first stage, a single Falcon 9 first stage being used as an SSTO, or single stage to orbit, and that turns out actually works. So I can show you the graphs that I've made here. This is the speed graph. It doesn't have staging, so the points where the acceleration decreases, it's not being staged. It's shutting down engines in order to regulate the thrust weight ratio, so it doesn't accelerate too hard, because in single stage to orbit mode without a second stage, without this additional mass, it can accelerate quite hard with all the engines running, and in order basically not to over G, I decided to shut down engines at this point, as you can see, and at this point it shuts down all engines to go into a cruise phase, and then later reignites one engine, and each time it accelerates faster and faster as it burns fuel and gets lighter. And then also here's an altitude graph and a few more interesting things. This is the graph of drag, so you can see where its max Q is. Now this isn't really ideal, and it's just a little for fun project, so I decided to try out launching with full thrust for once, so all 9 engines running at full thrust. and then going into a quite aggressive turn, turning over quite quickly and to some 30-degree pitch. Now, the Falcon 9 first stage is of course not an ideal SSTO, which is for the simple reason that it's not designed as an SSTO. That's not really a design flaw, it's just that is not the purpose it's designed for, and so it doesn't make a good SSTO, but it works. Now, for the reusability, in this simulation, it actually has enough fuel left to do a deorbit and a landing burn, so hypothetically that's a possibility. But it's gonna burn up on re-entry because it doesn't have the fuel left to slow down significantly, and so it's going to enter the atmosphere at orbital speed and probably burn up. But it shows that hypothetically, with a better heat shield, maybe a smaller and lighter rocket, it could be possible, and the Falcon 9 first stage is a built rocket that works in practice. So hypothetically, the building of an SSTO isn't quite impossible. Now, its payload capacity is very small, but it's actually not insignificant. It's not some 2 kilograms or something. It's actually 2 tons in this case. Now, again, I've used these nodes and the same basic simulation that I've shown you before. I can skip through it quickly again to show you how the basics of it work. Again, you have a basic starting point, and you start with location coordinates that are 0 and the radius of the Earth and the rotation of the Earth for velocity. And, well, I've explained this earlier on. It's basically a time step based numerical ballistic simulation. Now we can go down through these numbers and see roughly how the launch trajectory plays out. Now, I did do a cruise phase and a circularization burn because the Falcon 9 just has way too much thrust. If you remove the second stage for a single stage to orbit, it just has way too much thrust to weight ratio, so it can't do that ideal one burn orbital insertion. It has to do a cruise phase and circularization burn. Another thing I've added that I only started further down for the actual circularization burn itself. This was made only for the circularization burn. These 2 columns you see here popping up. These are approximately the sink rate or climb rate and the vertical acceleration. Now, initially you can use the coordinates and the speed coordinates for that because this is basically the climb rate at this point, but these are Cartesian coordinates, so as soon as you leave the launch site, this only becomes an approximation, because the Earth is of course spherical, so if you start going around the Earth, the direction that is up changes its direction relative to the absolute coordinate system. So this is the upwards direction or the vertical speed as long as you're above the launch site, but as soon as you start moving off the launch site or significantly off the launch site relative to the radius of the Earth, this is no longer really the climb rate. And for the orbital insertion where you're quite far away from the launch site, I wanted to know the climb rate because I wanted to end the circularization burn at a climb rate of roughly 0, and I wanted to end the circularization burn so that the vertical acceleration was positive. And so what I did was not go the elegant way and using basic trigonometry to convert these Cartesian coordinates to spherical coordinates and then calculate the climb rate. That would have worked and would have been more precise, but just because it's quicker, I've just used the altitude readout that I already had, which was already based on the spherical coordinate system because it's already using Pythagoras, and just did a derivation of that, and then I had the climb rate, and then I did a derivation of the climb rate, and I had the vertical acceleration. Of course, each time divided by time steps. So because it's using one time step to the next, so to get the acceleration in per second, you have to divide by the time step. And as I start the circularization burn here, you can see that the vertical speed is approaching 0 and the vertical acceleration is slightly above 0, which is what you're going for in a circularization burn, of course. Now, I did also use a slightly different drag factor from the earlier Falcon Heavy simulation, obviously, since the geometry of a single Falcon 9 core is of course different from a Falcon Heavy, so it has less drag. I've also assumed not a wide fairing, but a small pointy nose cone, so it doesn't have too much drag, and you can see, as I've stated in the beginning, that the drag to mass ratio, it briefly goes above 1 here, but then it doesn't go above 2 and it quickly drops below 1 again. So you can do a very shallow ascent rate with this and do a quick turn to the horizontal and quickly accelerate to orbital speed, not wasting too much delta V. Of course, we still have this delta V readout, and in the end it has used up 8,626 meters per second of delta V, or just before the circularization burn 8,373, which of course is also just a readout and doesn't affect the simulation itself. So again, I hope you found this slightly interesting. I have of course done a few videos as to how to make this kind of Excel table yourself, and as always, thanks for watching.